All right. Okay, so 100 Days of ML, it's day 91, and I'm going to be exploring the linear bottlenecks and the inverted residual layers of MobileNet. So I'm going to open up this paper here. I need a copy of this on my iPad, so I'm going to go ahead and download and upload this onto my iPad. Okay, so basically it would be section number, I believe, 3. Yep, so it starts over here, depth-wise separable convolutions. So that's the dys block over here, the 3x3 dys. And this layer of three layers with 1x1 conv2d, 3x3 dys layer, and a linear 1x1 conv2d essentially makes up what is known as the bottleneck residual block. And so I'm going to go ahead and read the section 3, preliminaries, discussion, intuition, which talks about the linear bottlenecks and the depth-wise separation convolutions, and also the inverted residual blocks. I'm going to try to get as much done as possible. Hopefully I'll be able to finish this section. But essentially I'm kind of short on time right now. Whatever I don't finish, I'll start up tomorrow morning. I'm just happy that, my finals are done today and I have a lot more time to focus on what to do next. So let me get this opened up on my iPad and I'll go ahead and mute myself while I take notes. Okay, so I mean, when we start off with the depthwise separable convolutions, it was kind of making sense to me that it's increasing the efficiency by k to the power of 2. So basically, when k is equal to 3, it's about 9 times smaller and more efficient than a standard convolution. But when it comes to these linear bottlenecks, I just don't understand where it's like going. Uh, it's talking about transformations and these manifolds of interests. But essentially, the fact that assuming that the manifold interest is low dimension, it can capture by inserting linear bottleneck layers. I honestly don't know what that means. I mean, we can see a visual representation of this implementation here, where some sort of linear bottleneck is inserted between these com blocks right here, and that's essentially being able to, I guess, increase the efficiency to some extent. But I don't know. Just don't understand the wording here. I don't know what to do about that. But for at least I guess I understand what's going on here. If I can implement this architecture, I could essentially replicate the residual bottleneck residual block, and this leads to the MD con block, which is implemented in EfficientNet. So what I'll try to do tomorrow is try to implement EfficientNet once again with the understanding of what these MB blocks are. So yeah, so I'll start with the regular con blocks and then I'll move on to the MB blocks. I think there's some pooling layers also involved, but that should be pretty easy and come standard with Keras. So here we go. We have the conv 3x3 and then a sequence of MB con blocks. I'll try to check if this MB con block actually exists in Keras. If it does, then it'll be easy to implement. Otherwise, we'll have to custom build it. And then finally, a conv 1x1 with the pooling. This should be pretty easy to add on. Okay, so that pretty much marks everything for today. Let me just go ahead update GitHub and go ahead and start up on what the heck? Never had that done before. Okay. What? This is actually annoying. All right, I'm just gonna commit this later. I'm gonna end the stream.